Hi everyone, I'm Brian Anderson from Team 3, and I will be starting off our term project presentation. Just a little overview of what we'll be going over today. We will be using the CRISP DM method to review our analysis. I will cover step 1, business understanding, and step 2, data understanding. My teammate Kelsey will cover data preparation. Sriraksha will be covering model building, and Don will finish us off with testing and evaluation and deployment. So without further ado, step 1, business understanding. The purpose of the business understanding phase is to develop a roadmap for the ensuing data mining process. Typically, a goal is established in this phase to guide the analysis. With this project, we looked at the severity of injury that occur in automobile accidents. Automobile accidents seriously injure or kill thousands of people every year and incur billions of dollars worth of property damage in the United States alone. While it is not possible to fully eliminate the number of automobile crashes that occur, it doesn't mean that the severity of these crashes can't be reduced. In order to better understand what factors, if any, affect injury severity, our team conducted an analysis of the data sets from the crash report sampling system provided by the National Highway Traffic Safety Association. This organization's goal is to reduce the human toll and property damage that motor vehicle traffic inflicts on our society. The goal of this study was to use the data to determine which factors resulted in serious injuries and how we might be able to utilize these results to mitigate potential injuries in future automobile crashes. On to step 2, data understanding. The data from the crash report sampling system is a sample of the car crash data from various crashes in which the police were contacted. These crashes involved any possible combination of vehicles, pedestrians, and cyclists within the United States. The data source for this mining study was provided in tabular form. Prior to the data cleaning process, the data set contained a total of 196 columns and 133,607 rows. The data set that we utilized in this analysis had a combination of 3 different variable categories provided by the National Highway Traffic Safety Association, including accident, person, and vehicle. So let's talk about those a little bit farther. The accident data could include anything from the number of persons in the vehicle, as well as the month, day, and time of day of the crash. Vehicle data could include vehicle year, make, model, body type, whether the accident was a rollover, and what kind of traffic control divide there was on the street where the accident occurred. The person data included the age, sex, and seating position, as well as any drug or alcohol involvement of the people that were in the vehicle. The software that we use to merge, clean, and model the data contained within these 3 data categories was 9. The majority of the values within this set were encoded, meaning a series of integer values were used in place of string values for each category. As part of the variable selection process, which Kelsey will describe farther in step 3, the data preparation section, variables which held lower levels of influence in predicting the severity of automobile accidents were gradually filtered out from the data set, although there were also a few variables which were filtered out manually prior to the beginning of the variable section. So while we were looking through the data, our team identified that some of the variables were irrelevant to making predictions to an accident severity, such as customer ID values or VIN or vehicle identification numbers. As such, in order to avoid any noise which might have otherwise been generated by those variables, they were immediately removed from the data set. I will now pass it off to Kelsey for data preparation. Thank you.
Before moving into the modeling phase, the data first needed to be cleaned and the total number of variables in the data set reduced. One example of a process used to clean the data was the replacement of encoded values which corresponded to nulls with nulls. While some of the process used in variable reduction included the removal of columns that were missing large amounts of data, as well as the removal of columns with no variance and those which were highly correlated. As you can see here, the shown 9 workflow contains all of the processes that were used in the data preparation stage. Starting from the left, joiner nodes were used to combine the 3 previously mentioned data files. Next, the target variable, injury severity, was filtered so that the data set only included rows with an injury severity value of 1 through 4, since the other values within this particular variable weren't relevant to our analysis. Afterwards, the data was once again filtered, this time based on the variable for seat position. The goal of this analysis was to predict the severity of injuries sustained by the driver and the driver alone, meaning we only needed to include rows where the driver was the one injured. The encoded value used to represent the front left seat of a vehicle, which is the driver's seat, was the number 11, so the rows in the dataset were filtered by this value. The next node in the workflow is what's known as a composite node, which is the node that's just been visually consolidated and contains multiple processes. The first composite node contained math formulas, which these were used to replace encoded values with nulls. Each variable in the dataset used a slightly different encoding scheme, meaning that we couldn't just use a single math formula node to correct all variables in the dataset. In order to analyze the amount of missing data in the dataset, these various null values were replaced with blanks, and then once we had done this, 9 was able to recognize which cells were actually missing data. Once all the variables in the dataset had been converted, columns that were missing at least 25% of their data were dropped from the dataset. As you can see from the next node, the target variable, injury severity, was then binned into 2 bins. One was a high bin, which contained injury severity values of 3 through 4, meaning cases that had either severe or fatal injuries, while the other bin, low, contained cases with low or mild injuries, so the variable values of 1 or 2. The goal of predicting cases with severe injuries was why the team decided to bin the target variable, since we weren't really interested in the differences between individual stages, such as, say, the difference between level 1 and 2, or the difference between level 2 and 3. The next node used was a low variance filter, which was used again as part of variable selection. The low variance filter was used to sort out columns which had 0 variance, meaning they had the same value throughout the dataset. If there's not any change to the variable, it really isn't much use to making predictions, which is the logic behind why such variables were dropped. Then, a correlation matrix and a correlation filter were used in tangent to drop columns with a correlation coefficient greater than 0.7 to avoid any issues with collinearity. So as of this point in variable selection process, there were still 57 variables in the dataset, which is a pretty great drop from the nearly 200 we'd started with. Since the team still wanted to reduce this variable value further, though, a forward selection loop was utilized. The forward selection loop uses a naive Bayes analysis and checks the accuracy of the model based on different combinations of variables. The forward selection loop was set to choose the 25 predictor variables which best provided an accuracy level for the model. The final variables which were selected by this loop are shown in the table below, called final variables. So as you may have noticed before, there were actually 2 composite nodes used in the analysis. The second composite node was used to convert the categorical variables remaining after the selection loop into string variables, since originally all variables had been made with encoded values, which means they registered integers. Afterwards, there were only 2 minor changes that were made before moving into the modeling phase. The first was to create a variable known as winter, which checked if the month of the accident was November, December, January, or February. The second change was made to convert the variable model year to a slightly more friendly format. This was done by subtracting the values of the model year column from the year 2017, which was the year the data was recorded. The resulting variables, which the first one was called winter and the second was called vehicle age, were both used in place of the original values in the dataset. As of this time, the data was ready to be exported to a separate file, which we would then import and use in creating the models. This method was used to prevent any kind of changes from occurring accidentally to the data preparation nodules used here, so they could be consistent with our outputs.
Hello everyone, my name is Sri Raksha Ravi Prakash, and I am going to walk you through the fourth step in CRISP-DM methodology, which is model building. For this project, we have used two models, which is logistic regression and artificial neural network from numeric-based model types, and two models such as decision tree and naive-based from set-based model types. Basically, logical regression is a statistical method used to predict an dependent variable, which is usually a binary variable. It can be dependent on other independent variables, which are ordinal, nominal, etc. Here, as our target variable is injury severity, so it is a variable it's a binary variable that of high or low intensity of the severity of the injury. And artificial neural network consists of input layer, hidden layer, and an output layer. So basically, the neurons in the layers are connected with the weighted edges. So each of these edges are summed, and an activation function is used to predict the value of the output variable. Coming to decision tree, it's basically a tree-like structure where each node represents a class, and a test will be conducted on an attribute, and based on the result of the test, the branches are developed, and so the internal nodes are basically the attributes. Then naive base is basically used for classification problems, and it is also used where the model should be simple, affordable, and scalable. Here, the target variable is injury severity, and we have to differentiate between the high level intensity of injury and low level intensity of injury. So this model can be used as well. So moving on to the next slide, we have the logistic regression and artificial neural network model. For these models, we have used category to number node to convert every category to an integer, as these models don't accept string variables. So the column filter was used to filter out other string variables as well. Only for artificial neural networks, we have used normalizer node, as lot of mathematical process was utilized by this model. Then for both of these models, we have used the X-partitioner node for k-fold cross-validation. That is, 10 folds was used to classified groups. Basically, this k-fold cross-validation is used in machine learning models uh, to have a robust model. So the whole data set is divided into k splits of data, and each data will be tested and trained so that it will be less biased and will give more optimal results. After this, the X partitioner node is connected to a smart node which is used to balance the number of records from both high and low bins of the target variable. This is then fed into the logistic regression learner and the logistic regression predictor and multi-layer perceptron learner and multi-layer perceptron predictor respectively. After this, X aggregator node is used in tangent with the X partitioner to complete the cross-validation loop. Also, we have used the ROC curve to obtain the ROC curve and the scorer node to obtain the confusion matrix. Here in this diagram, on top of the red line, it is the logistic regression model, and below is the artificial neural network model. Okay, moving on to the next slide, we have decision tree and naive-based model. Here, we have used the actual categorical variables for building the model, and similar to the above two models, we have used the X partitioner node, smart node, decision tree learner and predictor node, naive-based learner and predictor node respectively, aggregator node, and ROC curve node and scorer node. In this diagram, the top of the red line represents the decision tree model and below is the naive-based model. Here, the aggregators are connected to a joiner which is then connected to a ROC curve node. So, this ROC curve node gives us the ROC curves of 4 different models so that we can view it together in a single graph. So in the scorer node, when we obtain the confusion matrix, from this confusion matrix we'll be able to decide which model is doing the best. The confusion matrix has the variable accuracy which tells which model is doing the best in predicting the target variable injury and severity. Next, Don will talk about the evaluation and deployment process of CRISP-DM methodology.
Hi, this is Don Whalen with Team 3 from the distance learning student groups. And I'm going to talk about testing and evaluation and deployment. So, let's start here. So, in order to determine which of our 4 models was best able to predict accidents with severe injuries, so those with a designation of high in our injury severity binned column, we used ROC curves and confusion matrices for each of the models, and we had an aggregated one at the end. So based on the ROC curve, the neural network performed the best. It was best able to distinguish between high and low and predict. However, if you look at the confusion matrices, which we will in a couple slides, the decision tree gave us the most accuracy. So, and as you can see here, let me make this a little larger. There we go. So, as you can see, the blue line here is the neural network. It came in at 0.9197% accuracy, so almost 92%, which is very good. Coming in second place, logistic regression, the red line, and you can, the numbers here tell it, but you can also just tell that there's more, the most area under the curve, literally for the blue line, and then descending all the way to the green line. But for the red line, logistic regression, a little bit behind neural networks at 0.9097, almost 91%, still very good. The purple line is naive bias, came in at 0.8885, almost 89%. And the worst of all was the decision tree, which was at 0.7553. The tough part is that with the neural network, you get the black box effect. So it's tough to tell which factors contributed the most. But let's move on. And if you're looking at the confusion matrices, the best performing model was the decision tree at 85.963% accuracy. Interesting enough, because the decision tree, as we just saw, performed the worst when looking at the ROC curves. So, but looking at the confusion matrices, second place was neural network at 85.805%. Then logistic regression at 84.746%. And coming in last was naive bias at 78.235% accuracy. And this is a snapshot of the 4 confusion matrices side by side. And you can see those figures here again. So 85, very close, 84 and 78. Let's see. And getting into the deployment phase, it's the last step in the CRISP-DM process. It's also the most important one. So we've run the models, we've gained the information, and it's now time to act on them. So decision makers, lawmakers can use this data to hopefully minimize the risk of severe injuries, so fatalities and severe injuries in automobile accidents. But it has to go a step further. So the maintenance of these models is very important. So it needs to be determined how often new data will be gathered and new models will be built, tested, and run, so that these decisions aren't just made one time and it's decided this is what we're going to do, but how are we going to continue to make sure that we're protecting people on the roads, protecting everyone with the most current data. So the deployment phase is where we present this information to the decision makers, and it's up to them to decide how often they want to renew this project so that we're keeping everyone safe. This information can be used in order to educate the public and potentially influence car production companies and government agencies that work with roadways. Thank you very much.